Hello everyone, and welcome to this video where we discuss mathematics and physics on the board. This video is the final video of a series where we try to actually calculate the Hodge dual for one forms, two forms, and three forms. And so in this particular situation, what we are going to do is precisely look at the case of three forms of three vectors. In this particular case, I'm not necessarily distinguishing the two. Now, I'm going to assume some prior knowledge about the previous videos, in particular, what happens when we try to evaluate this bilinear map in the case of multiple, where k basically is different from 1, so it can be 2, 3, etc. And in the particular case we are looking at. So basically that's what we're going today, and then we will basically complete this particular table where we've got all the relationship between the 1, 2, and 3 vectors with their corresponding dual. Right, okay, so let's summarize a bit what we have here. So here, I'm not going to reread this. In principle, you may have followed the previous videos. If not, I'm going to put the link there for 1 and 2. But otherwise, here we simply use this particular signature in the vector space R cross R3, and basically that's it. And importantly, we use this bilinear map in the vector space of the so-called k vectors or k forms, and basically from there we define the Hodge dual as being like this, and returning a prefactor here that is in front of the so-called canonical volume form or volume kind of vector. Okay, so here I've preamply like filled in part of the work here. So the only thing I'm saying is that when k is equal to 3, we've got to name things and expand them onto the basis. And again, here we need to do that for alpha, beta, and for the Hodge dual as well, which has to be, by definition, the Hodge dual has to be of like a dimension or a degree which is n being the total dimension of space minus k. So here that's going to be 4 minus 3, which is kind of 1. And so we are dealing with one form or one vector here. So essentially that's kind of what I said, and I wrote beta tilde is the conventional notation I use in this video series to denote the components of the Hodge dual, just because carrying the star everywhere, I don't find it very convenient. And basically that's it. Now, the only thing I want to stress here is this particular line. If you actually manage to watch through the entirety of the video for the k is equal to 2 k's, then you probably realize it was slightly laborious. But one of the reasons is because I didn't right away. I mean, we need to kind of work a bit to appreciate that essentially if you have any three form with any three form here that are related to the product of the e's, okay, which correspond to the canonical basis here, then because they correspond to the pseudo or quasi Euclidean metric, which is kind of here, this kind of Minkowskian, with this particular signature, it means you've got plus and minus 1, minus 1, minus 1 along the diagonal, and then you've got 0 everywhere as far as the inner product is concerned. Consequently, if you actually have anything like this, you're going to find 0 if essentially the former form is not simply plus or minus the other form here. Okay, so essentially that's kind of what I mean. And when I say plus or minus, it's because I'm allowing myself to think that you can swap these guys, okay, and you're going to get plus or minus signs there. Okay, so that's basically how it is. So here I'm allowing in this equality here I'm allowing you, for example, to swap these things around if needed, so that you can get this kind of plus or minus equality. Okay, so what that means, therefore, and I'm going to start by first evaluating this particular quantity, which is f alpha beta, is that then I can get rid of tons of actually null terms, and the only terms that are going to be non-zero are as follows. So I'm going to get alpha 0, 1, 2, and then beta 0, 1, 2. And then f, I've got f of E0, E1, E2, okay? Now, the thing is that basically, the numbers I'm going to get along the diagonal of the matrix that I need to work through here are going to be +1, -1, -1. So essentially, I'm going to get 1 times -1 times -1 when I calculate the determinant. So I can write it here like this. So that's going to be, I can write it like so. So that's going to be 1, -1, -1, and 0 anywhere else. And then I can continue doing the same thing here. So that's going to be alpha 1, 2, 3, beta 1, 2, 3. But then in that case, I've got -1, -1, -1, and then zeros here. And then I've got plus, where am I? Plus alpha 2, 3, 0, beta 2, 3, 0. And then here I'm going to have -1, -1, and then +1. And finally, the last one would be alpha 3, 0, 1, beta 3, 0, 1. And then that's going to be -1, +1, -1. And again, 0 there. So consequently, this is going to be equal to alpha 0, 1, 2, beta 0, 1, 2, then times -1. So I put a minus here. Then here, this is a plus, so plus alpha 2, 3, 0, beta 2, 3, 0. Then, okay, so that's this plus here. I forgot this one. Apologies. So here it's a plus. Here this is this one, and I forgot the -1 here. Alpha 1, 2, 3, beta 1, 2, 3, and then we have plus alpha blah, 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 where are we? This one here, and that's actually a minus sign again. No, sorry, a plus sign again. So this is giving us plus alpha 301 beta 301. Okay, so that's for f of alpha beta, out of which I basically get the following. So alpha wedge star beta, alpha wedge star beta is therefore going to be equal to all that. So alpha 0, 1, 2, beta 0, 1, 2 plus alpha 2, 3, 0, beta 2, 3, 0 minus alpha 1, 2, 3, beta 1, 2, 3, and then plus alpha 3, 0, 1, beta 3, 0, 1. And all of that is actually E0, E1, E2, E3. Okay, so that's one expression that comes from there. Now, what I'm going to do is essentially try to see what happens if I actually carry out this particular expression with the expression here for the components of as the Hodge dual. So I can also have that beta here is going to be equal to, so let's look. So alpha wedge star beta So of course that's not going to work because it contains E0. So as soon as it contains E0, that doesn't work. So alpha 1, I need to simply complete with E3. Okay, so I'm going to have alpha 0, 1, 2, beta tilde 3, and then I just need to put things a bit in perspective here. But no, okay, that's going to be E0, E1, E2, E3. Okay, and I'm just trying to find out where I can write stuff, to be honest, because I don't want to erase this final one. So I would like to keep it if possible. So I'm just going to continue, and then after that I'm going to erase here, and we are going to start again. So the only part I need to keep is this one. And then I also need to keep the continuation of that. Okay, so then I will erase that and we'll start again. So let's continue for now. So then we've got plus alpha 1, 2, 3, 1, 2, 3, and then what is missing is 0, so that's going to be beta tilde 0, and that's E1, E2, E3, and then E0. Then we've got another one, plus alpha 2, 3, 2, 3, 0, and then that's going to be beta tilde 1, and that's E2, E3, and then E0, and then E1. And I'm going to put the final one here, so that's going to be alpha 3, 0, 1, and then beta tilde 2, and that's E3, E0, E1, and then E2 here. So now I'm going to erase and we'll see each other in a bit. Okay, so let's continue. So I've written the first term because I know that the first term is directly written with the volume, like the canonical volume form, so that's perfectly fine. But then we need to find out again what kind of permutation we need to do. So here we are there, and what I need to do is move the E0 across. That's the same manipulation we had to do in the second case, k equals 0. In fact, we had to do the k equals 2, and we did the very same one as well in the case k equal 1. So the bottom line is that we carry out this E0 progressively to leftwards. So we've got a first step here, a second one, and then a third one. And so each time you capitalize a minus sign, so that's going to be minus alpha 1, 2, 3, and then beta tilde 0. Now let's see how that works for the other. In that case here, we need to be a bit careful. So I'm going to swap E3 for E1. Okay, so I'm capitalizing one minus sign here, and then E2 for E0, and I've got one minus sign here. So the bottom line is that I've got a plus alpha 2, 3, 0, and then beta tilde 1. And then here, I'm going to get to do the opposite of what we did here. I need to carry rightwards E3. And so the way I do that is via 1, and then 2, and then 3. And so I'm going to have a minus sign per operation of permutation. And so here I'm going to get minus alpha 301, sorry, and then beta tilde 2. And so I've got here E1, E0, E1, E2, E3. Okay, and what I want to do is compare it to this particular expression. So the what I get when I do that is I look at what is in front of alpha 0, 1, 2, because this is supposed to be true. This equality is supposed to be true for any alpha. Okay, so it's not like something that can happen accidentally. And so in front of alpha 0, 2, I've got that beta tilde 3 has to be equal, therefore, to beta 0, 1, 2. Okay, So that's what I get. Then here I've got that minus beta tilde 0. That's what is in front of alpha 1, 2, 3. So alpha 1, 2, 3 here is minus beta 1, 2, 3. Then we have beta tilde 1. And that's in front of then alpha 230. So alpha 230 is here. So that's beta 230. And finally, we have minus beta tilde 2 has to be equal. So that's in front of alpha 301. And so that's beta 301. Okay. So then we can look at the different kind of expressions. So here, let's say, so I'm just going to do something very similar to that. So let's say beta is equal to E0, E1, E2. Therefore, star of beta is equal to star of E0, E1, E2. And what we have is that we've got that beta 0, 1, 2 is equal to 1, and that corresponds to beta tilde 3 equals to 1. So that's going to be equal to E3. Okay, so let's continue. Beta is equal to E1, E2, E3. Then we've got that the star beta is equal to star E1, E2, E3. And what we have is that we've got 1 for beta 1, 2, 3, and that's going to be equal to beta 0. So that's actually E0. Then beta is equal to E2, E3, E0. So the star of that is equal to the star of E2, E3, E0. And basically I look, beta 230 is equal to 1, so beta tilde is equal to 1. So that's equal to E1. And finally, we've got beta is equal to E3, E0, E1. And then we've got that the star beta is equal to star of E3, E0, and then E1. And what we have is that beta 301 is equal to 1, and so it's equal to, so beta tilde 2 is minus 1, and so it's going to be equal to minus E2. Okay, so essentially that's what we have. We have these particular relationships here, and that's for k is equal to 3. Now, one thing that is quite interesting to look at is what happens if I actually carry out the star dual operator of a star dual operator. Okay, and what you're going to notice is that there are some kind of minus signs that can appear here and there. For example, here you've got that the star of E2 wedge E3, okay, is actually E0 wedge E1, okay? But if you actually take the star of E0 wedge E1, you actually get minus E2 wedge E3. So there is, basically it's not involutive, there is a minus sign actually comes in this particular situation when you introduce the double kind of dual. Likewise here, if you've got the star of E3 wedge E0 is actually E1 wedge E2, but if you take E1 wedge E2, you've got minus E3 wedge E0. So in the case of this particular kind of two forms, the dual operation, so the applying twice the Hodge operator, is going to be like pseudo-involutive, where you get a minus sign from it. Okay, you can try for the other pairs. Let's try quickly this one here. So E1, E2, is going to give you, and maybe actually it's not going to work, we'll see. So E1, E2 is going to give you minus E3, E0, okay? But then if you actually take the Hodge dual of E3, E0, you're going to get minus E1, E2. Okay, so again, you're actually going to get something with minus sign. So what we can see here is that this is pseudo involutive, in the sense that if you have one of these two forms, you've got that star. If you're one way of saying it, star is equal to -1. Okay, so that's kind of the idea. Now you can try to check what's going on in this particular case by looking at k is equal to 1 or k is equal to 3. So for example, if you take E naught, the star of E naught is E1, E2, E3, okay? And then the star of that, E1, E2, E3 is this one, and that's E naught itself, okay? Likewise, if I take E1, the star of E1 is E2, E3, E0. And then if I take the star of E2, E3, E0, that's actually E1. Okay, so the bottom line is that in this particular case, I actually get the same. Okay, and then if we look at this one, then we are going to get the same because we get a minus sign for E2 here. So we are going to get this particular involution. So here, actually, this is involutive. So it depends what forms what the rank of the forms you are actually applying it to. So involutive, and so what I mean by that is that the star is actually equal to 1. So applying double the Hodge dual to these three forms or to this one forms is going to be involutive. So is equal to 1, so that's involutive. Now note that this kind of results may depend on the signature you choose here. If you choose to use minus, plus, 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 the kind of rules we've sorted out here might be a bit different. Okay, so keep that in mind. But otherwise, these are the rules for getting the Hodge duals from the basic definitions of how to get there. That seems, I mean, it is a bit complicated. It is a bit tedious. It's not complicated to do. You just need to go along, try to make sure you've got all the basis vectors, and then kind of work it out. Now, the general formulas can be worked out as well in some general form, depending on 3 forms and 1 form. But to be honest, it actually looks complicated to implement. And I think it's more straightforward to go a bit more slowly, more in a pedestrian way, and then actually go on with it. And at some point, eventually, we'll get there. So that's it. If you've got any questions, please let me know. We are going to use these things very soon, or at least clearly in a later video, where we look at how this can be used in electrodynamics.